So I don't know how to decide the EOP for you guys, because each of you actually, when you are deciding where the ground coordinate is, it will be different. Some of you may set starting from the 0. Some of you starting from 10,000 or something. So everyone will set different coordinates, ground coordinates. So your EOP should be decided accordingly. But however, as you can see, we have the requirement, which is the omega phi kappa less than 3 degrees. So which means that we want to simulate a vertical photo. Vertical photo. But if you want, you can do the tilt photo and do some analysis, and that will be interesting as well. Okay, so that's the procedure I just mentioned. So it should be fine. Till now, what you are getting over here, these image coordinates, it's like the perfect image. It's like the perfect image that fit with your image geometry perfectly. So, but in reality, of course, that's not the case. In reality, that's not the case. So what we want to simulate is a little bit more realistic image. Then in this case, what we are doing is we add some random error to it. We add some random error. Let me write it over here. This way. Okay. So random error. Right, random error. Then in this case, you have a new set of image coordinates. So you may slightly change where those image coordinates are. You may slightly change that. So by adding the random error, then you can have the new set of image coordinates. X and Y with arrow. Alright. So how to do it? First of all, you have the image coordinates already, and then right now we want to add the random arrow. So this random arrow, what we require you to do is to have the random arrow following normal distribution, right? Following normal distribution. So in this case, how we are going to do that? So as you can see, we want the arrow with this normal distribution, which has the mean value as 0 and the sigma as 9 micrometer. Right, so that's the normal distribution that we want. Okay. When you see this, actually, like I said, I believe I talked about this before. So when you see that, which means that you want to simulate random errors with this. This kind of normal distribution, and by following this normal distribution, then you are going to pick the random error. So, in terms of the normal distribution, of course, you guys know it. Most of the error, samples, they will be concentrated to the mean value, and some of them they are scattered. So that's the error that we want to simulate. So how to simulate it? The way you can simulate it in many ways actually. Some of the tools actually in different programming language, they can directly give you the random error following a certain normal distribution. So if you can find that, of course, you can directly use it. You can directly use it. But if you couldn't find that, then what you can do is usually the random error is the equivalent distribution. Is right, it's like this. This is a normal distribution, right? So equivalent distribution is more like everything has the same chance, has the same. This is still probability density. So for example, it's like when you roll a dice. when you roll the dice. So when you get 1, 2, 3, 4, 5, 6, so each of them has 1, 6. So 1, 6 chance, right? Yeah, to get different number. So that's the equivalent distribution. 中文叫平均分布吗？还是什么？平均分布？我忘了。Anyway, so I'm trying to remember what's the name for that distribution in Chinese. I'm just trying to remember that, but I forgot. Alright. So anyway, so usually if you couldn't find, like I said, if you couldn't find a function that directly give you a certain normal distribution, then you can use equivalent distribution random number generator to simulate the normal distribution. And you can do that because normally and usually what the random number generator, the function for the random number is usually following the equivalent distribution. Right? So usually it's like that. So how to use that type of random number generator to simulate the normal distribution? You can do that by following the central limit theorem. You can do that by following that. So what that is? Oh, in Chinese, this is called 中央极限定理。定律，中央极限定律。Yeah. Right. So central limit theorem. So let's take a look at what that is. So okay, let's say we have the image coordinates x1, y1, and to the x and to yn. So we have we have 2n arrows. We need to simulate 2n arrows. Now the number of arrows that we need to simulate is 2n. So in this case, we can have the 2n random arrows over here simulated. So the first thing is I can use the equivalent distribution random number generator to generate a lot of values. I can use that to generate a lot of value. Okay? And so for example, in order to decide the first arrow, I simulate m values first. I simulate m equivalent distribution random number first. For the second arrow, I also simulate m numbers, and so on and so forth. So then what I'm going to do is to take the average. I'm going to take the average for these m values and to get the v1. Similarly, for the second row, I take the average for the second row and then get the other value, v2, and so on and so forth. So I have v1 to v2n. What you can do is you can try to see the differences. For example, if I simulate the m with like only 5 or to like 100, 500, 200, so you can try to use different number of random numbers over here. Right? You can try to use different numbers of random numbers over here. The central limit theorem is that originally you have the equivalent distribution. But if you have enough set of number, and then you take the average, and then you take the average like this, you take the average, and then this v1 to v2n, you will follow normal distribution. You will follow normal distribution. For example, like I said, roll the dice, right? So when you roll just one dice, then you will be equivalent distribution. But right now, if you have 100 dice, and you roll it, and you have 100 number, take the average. Then second time, 100 dice, roll it again. You have the second, take the average, you have the second number. And the third time, the fourth time, and so on and so forth. And those averaged value will form normal distribution. Those average value will form normal distribution. Why? You can imagine, the chance that you get 1, 2, 3, 4, 5, 6 when you roll one dice, just 1/6 chance. But when you are calculating the average, then in this case, most of the value after you take the average, most of the value will be close to, for example, 3. There's 1, 6, so 3.5, right? So in this case, and because it's an equivalent distribution, so after you take the average, so most of the average value will be over here, But of course, there are some extreme cases. So some of the value will be have a less chance to be a smaller value, have a less chance to be a larger value. But in general, you will get something similar, very similar to the normal distribution. That's the central limit theorem. 中央极限定理就是在讲这件事。Okay. So if, like I said, if you couldn't find a function for you to directly simulate the normal distribution, then you can use the equivalent random number generator and simulate those equivalent random numbers, and then take the average. Then this set supposedly should follow normal distribution. Of course, different number will affect that. If you only have a smaller number to take the average, then, or you have a larger number to take the average, of course, right? Of course, supposedly, larger value will give you a more stable normal distribution. Right? But however, I encourage you guys to try it. Right? I encourage you guys to try it and then see what the normal distribution will look like with different sets and different number of values over there. Okay, till now, any question? Any question? If not, then, however, our requirement is to have something like this. Our requirement is this. The average value is 0, and the sigma is 9 micrometer. So that's our requirement. But this set of data, they are generated randomly. So of course, their mean value won't be exactly at 0. And so you have a mean value at V, and you have its own variance. It has its own variance or its own sigma. So in this case, how can we transform this distribution to this distribution? So if we want to change this normal distribution to this normal distribution, how are we going to do that? The way to do it is over here. It's over here. So for each of the value v1 to v2n, so we are going to divide. We are going to deduct the mean value. So it's like shift. It's like shift originally, like I said. Let me use this. Right. So after you use the central limit theorem, and you get a normal distribution like this, but this is not the normal distribution that we want. So what we are doing over here is first we shift as you can see, we minus the average. So we kind of like shift this normal distribution to here. And we shift this to here. However, the size of the sigma are different, right? So we need to sketch it. We need to like enlarge it or shrink it so that it fits to the sigma that we need. Right? So we shift it and change the size of it. So how to do that? First of all, each of the value, each of the sample needs to be like deduct the average value so that it moves to the 0 as the average, and then you like divide it by sigma, the original sigma over here. So which is more like normalization? You normalize it, and then after you normalize it, then you multiply the design sigma. Right? You multiply the design sigma. Then in this case, you can have the normal distribution that you want. Yeah. Should be easy to understand. So yeah, like I said again, you have one normal distribution over here, and because it's not exactly like the normal distribution that you want, so you are going to shift it and then change the size of the normal distribution, then you have the normal distribution, the normal distribution that you want. That's it. Okay. So this part, any question? Okay, good. So, and here, as you can see, the procedure generates a series of render arrows that follow this normal distribution. And the next thing is add the normal distribution to the image coordinates. Then you have the image coordinates with arrow. And how to do that is just like this. Just add the render number to the image coordinates. Directly add them. Okay. Okay, any question? Should be fine for this step, right? Right, that's good. Okay, here is the part that will be interesting. Okay, so the next step is we want to try. Okay, this is probably the part that you may not be able to understand intuitively. So right now you already, you can say, polluted by the knowledge. So you already know that the image space and object space, they have the relationship, the image geometry.